It is a beautiful sunny day and it's ready to do some chemistry. We left off talking about light behaving as a wave and the electromagnetic spectrum, kind of looking at the speed of light, that sort of stuff. But when we look at the behavior of the electron, there's more going on there, and it really kind of stems from kind of this idea of how energy works and how things move. So when you heat something up and it changes color, when you think of like the element on an electric stove, or when you think of when you heat up metal really hot, like under a Bunsen burner, it starts to glow. And that behavior is not easily defined by just having the wave nature of light or using the wave nature of light to describe it. So this led to this observation or phenomenon, Max Planck, which we'll get into Planck's constant, kind of explain this by really defining energy as coming in specific packets of energy. So rather than just kind of this full spectrum of energy, it's delivered or kind of comes in certain quantities or quanta. So that kind of leads us to looking at energy being both a wave and also this idea of a particle. So Einstein used the assumption to explain the photoelectric effect, and what the photoelectric effect is the idea that you can have light energy come in the form of a wave, but then it's able to remove or cause electrons to come off of a surface. So your idea here, the first image on the left of just kind of a metal surface, you've got radiant energy coming in. Let's just say sunlight. It comes in contact with the metal, and then you have electrons being emitted off. Electrons are coming off of that surface. So there's something going on there, and which was called the photoelectric effect. And then the same idea of having like a chamber that's completely empty of any gas, and then you have a metal surface and another surface to detect this movement of electrons and actually get a current. So this movement of electrons across a totally void space, it's got no other elements in it, and you're seeing this movement of electrons. So this relationship was concluded that the energy is proportional to frequency. So energy is equal to h, which is Planck's constant, or 6.626 times 10 to the negative 34th joules seconds, times the frequency of the energy coming in, the radiant energy coming in. So we can actually take this equation of energy and connect it with the other equation that we've utilized already. So if we know the wavelength of light, we can calculate the energy in one photon or packet of that light. So light behaves as a wave, but it also behaves as a quantized or specific pattern or packet of energy, and that is dependent on its wavelength. And this will lead us to when we look at the line spectrums or talk about the line spectrums of specific elements. And that is where we're going to leave off. I will see you tomorrow in class.